Welcome back. Okay, Charlie. Next to last day under these conditions. I'm supposed to come back Monday, so thank you for putting up with this. And thank you for turning in your first exam. I'm waiting on that from half of you still. Regardless, let's see, what do I want to say? Well, we're going to do some review, and we're going to do a little bit more of Dirac notation, and I'm sure I can convince Mrs. Charlie to get out of our way. We're just going to do more advanced stuff with Dirac notation, including learning a little bit more about matrices and column and row vector representations. And we've got really another week or so of this, and we're still kind of just learning ground rules and whatnot. As soon as we get out of this, we're going to start covering uncertainty principles, which of course is a big deal. Okay, it's really one of the most important things about quantum mechanics. Okay, so let's review from last time. All right, now one of the most important things I could ever cover is, of course, the resolution of the identity. This thing, the outer product of all states within a particular basis, right? So this would be all the harmonic oscillator wave functions. These are all the particle in the box states. In spin, this would be spin up, and spin up is n equals 1, spin down is the next state, and this is equal to 1. So all the times you can use the number 1, you can use this. Okay, so where that's useful is, let's look at the inner product of a normalized inner product of a state with itself, and let us insert the resolution of the identity. Now, where to insert these if you get confused, again, just the more we do it, the more you'll do it the right way every time, just with practice. Okay, so we insert that in between the bra and the ket, and what we end up with, of course, is I recognize this as a number, and I will call that the projection of the alpha onto the a to the n state. Maybe, again, that's a particle in a box state, and this ends up being the summation over all possible states within the Hilbert space. This is the coefficient, that is the complex conjugate of the coefficient, so this is the absolute value of those things, and of course they sum up to 1 because I projected a state onto itself. How could that be anything other than 1? All right, the last thing I want to cover is for an operator acting on its own eigenstate, you better get an eigenvalue times the state comes back. This is the standard eigenvalue equation. And of course, if the A operator is Hermitian, then this number is real. Okay, so therefore, a function of that operator acting on that state, any particular state, I'll call that A to the n, so that's the ground state, first excited state, whatever, is equal to that same function of the eigenvalue, of the resulting eigenvalue. And I think I messed this up in my notes yesterday. Of course, the ket is still there. That's the standard eigenvalue equation. So the point of this is that it's really easy. It's like kind of intuitive, right? So, I want to tell you, you can always let your intuition take the driver's seat, but that's not really true. This time you can, but sometimes you can, sometimes you can't. Okay, let's see. Now, what I want to do today is, now let's do some new material. Let's do some more. Let's do some matrix work, and let's do that with resolution of the identity. And what we're going to start are with kets, and then we're going to do matrices, and we're going to do bras. All right. So the alpha state, and I'm going to introduce a resolution of the identity. And you've actually seen this a couple of times at this point, but why not? Okay, so again, it's pretty easy. And we recognize this as an inner product, which is a coefficient. And so this ends up being the summation over all possible states Okay, so this is the representation for the alpha state. The representation in this basis, this A basis, which again, let's say it's particle in a box basis, is this. And we know that these coefficients represent how much of the alpha state is in particular A to the n state, right? That's because this is the projection of alpha into any particular arbitrary A to the n state. Okay. Let's see here. Now, what we're doing here is you're mostly learning rules of Dirac notation. So I don't know that you can necessarily just figure out some of the things I'm saying. Let me get the lights here. Okay, I just noticed that those shadows are probably kind of awful. There we go. Okay, a little bit better. Let's see here. Okay, so for Dirac notation, okay, so again, we're not like deriving things because I'm just kind of showing you still how it works. Therefore, the state alpha, based on what I've shown you, is technically a column vector, or a one element matrix. So probably not good to call it a matrix. It is a, oh really? Oh, hey kitty. All right. Yeah, I know, this is interesting. More interesting than what you got going on. Anyway. Okay, so it is a column vector. Okay, I guess I can close the vector if I have 3 little dots there. All right. Now, if you know what, if you've been given some solid information, notice that I'm being very abstract here. If you have well-defined states, then you should have a bunch of numbers, right? And of course, these coefficients are numbers. Okay. Now, why don't we do some things? Let's do some things. Give some concrete examples, right? Put some hard numbers down. So here's an example. Okay, so let's do the SZ plus state. Okay, and let's see. Let's put that in this representation. We have a certain weighing factor and a and the corresponding state. So we're going to do a sum of states, and in this case, I know this will be a little funky, but I've only got 2 states. The entire span of states is just 2. There's a plus and a minus state, right? And I've got some kind of coefficient, and then I've got the state. And let's see. In this case, how do I do this? Since I'm talking about the plus state, then I've got 1.0 times plus. And this is our shorthand from now on. And the weighing factor for the minus state is 0. Right, so there you go. Okay, now in a column vector, that is 1, 0. 1 and 0. So there you go. All right, not much to it. Okay, now, so this is kind of childlike. You've seen this, and the thing is, when I show you examples like this, I don't know that you learn a lot because it's painfully obvious, right? I mean, I'm describing a basis state, so remember that this is actually plus. I'm just using shorthand right here. It's like so simple you don't really learn anything when I give an example this easy, right? Okay, so instead, let's do Sx plus, right? Okay, now we're going to do something a little bit more complex. All right, now, at this point, I am just going to go jump to the weighing coefficients, and there's only 2, so this is going to be a 2-element, let's see, plus Sx plus and minus Sx plus. So what is that? Okay, now let's recall that let me make sure. I'm halfway looking at the paper, half looking at the camera. Okay, so recall that we determined from the Stern-Gerlach experiment that this had to be true. Now remember that we just kind of figured this out based on the results of the Stern-Gerlach experiment. We didn't do any derivation. This just simply matches our observations. Okay, so in that case, what this has to be, let's see. If we act on the left with a bra, then this element is the top one, so that's 1 over square root of 2. And then the next element, the minus ket, that's nothing, but then that survives, so it's 1 over square root of 2. And the way you would generally represent that is 1 over the square root of 2. And you may recall that I've shown you this, but now this is where it's coming from. All right, so anyway, and then if this was x minus, I think that ket, I'm kind of speaking out of my rear end here. I'm pretty sure I remembered. I just wanted to show you another example. -1 and 1, I believe, were the examples for xx minus. And then for y, there's an I in it, but I won't worry about that. I think you've seen enough. All right. Okay, so, yeah, whatever. So kets are column vectors. They're really simple. All right, now let's up our game a bit. Let's do an operator. All right, an operator. To turn an operator, the purpose here is to turn into a matrix. We do a double resolution of the identity. And I think I showed you a little bit of that last time. And I'm going to still use my N notation. Of course, when it applies to spin, there's actually only one, the upper and the lower element, but when it comes to a particle box, there's an infinite number. You've got to keep track of, I'm going to do a resolution on the left and right, so I have to have 2 resolutions of the identity. So it's a little funky because I'm working, the left and right are in the same basis. So I've got to do some cleverness. I've got to keep little dashes or something like n or an n prime. Okay, here's the operator. Now I've got just regular little n with no dash, n with no dash, and flub there. Okay, all right, let's see here. Now for 1, what I'm seeing here is an outer product, right? There's this, and then there's this, and this is really an inner product. Remember that the operator will do something to this state. It will return a value and another ket. So just never forget that these are still kets, right? If I'm going to associate the operator, if I'm going to let the operator act on the right on a ket, it's still a ket. Okay, that means that I've got a bra and a ket, and that makes that this is still an inner product. Okay, meaning that this is a number. So again, let's break it down. The operator is still an outer product. Outer products are operators, and this looks like it's just got some numerical weighing coefficient for that. All right, so what? Okay, now let's turn that into a matrix. Oh, I'm sorry I have this on two different sheets of paper. That's a little annoying, but I think you can follow along. Okay, so the operator in matrix land, I don't know how far I'm going to go down. Let's see. You know what? You really do need to see. You really do need to see the representation. Let me write that down. And prime equals 1 to infinity. You're going to have a little trouble. I thought I could be clever and do this on 2 different sheets of paper, but no, that's not going to work. So I'm just writing the same thing down again. Okay, the reason I really needed to write that down, what I want you to see is that this guy is on the left. Okay, so the sum begins with a 1, so that's like a ground state. Here's the operator. Now how do I know what's on the right? Well, it's the first element. So these have to be, it's the first element and it's on the diagonal. So these, the left and right parts better be the same. Okay, now I'm going down. And I can clearly associate this n prime with this, the part on the left. Okay, so let's do the next one. A2, because what else are you going to do? Operator. Okay, if I've changed the bra here, then the ket better be the same, right? And that's because if you're thinking like, oh no, there, it's A2, A2. No, A2, A2 is the diagonal element, right? Diagonal elements ought to be symmetric. Okay, so A1, A1, A2, A2, that makes perfect sense. And now notice that by process of elimination, I know that it's the ket that's moving, that's increasing across, going across to the right. So going down, the bra is increasing, the n prime deal, and going to the right, the ket is increasing, the n deal. Okay, there you go. And let's see, that means that this is A1, operator A to the n, and this is A to the n prime, operator A1, this is A to the n prime, assuming that there's a finite, this matrix is going to be pretty big if there's an infinite number of states. And then I can close off the matrix there if I've got these little dots that say, you go infinitely far. Okay. Obviously, you can't really do matrices if you have an infinite number of states. All right, so that's what that looks like. I need to cover some other identities here. And then we'll do an interesting example. Let's see, the first one is the matrix elements themselves. Let's do the book loves to use multiple dashes and, dash dash for 2. That's a big mistake because the book is never consistent whether it uses like a 2 or 2 dashes. Anyway, it throws me off quite a bit too. I've had to be careful when I wrote my notes to not do that, to try to be as coherent as possible. Okay, so now you may notice that I have simply switched the 2, and I think I have actually made a mistake. That's got to, in my own notes I'm looking at, there's got to be a little complicated. No, go away, Furbeast. No, Charlie. No, not now. Not now, Charlie. She's about to eat the camera. Anyway, I hope this is entertaining. Now let's see if Hermitian. Charlie, no, come on. If Hermitian, you see my handwriting suffering, this cat's in the way. Then what you have is A2 sigma prime is equal to A prime. Okay, notice that I didn't do the operator any different. Okay, now what that means is that off-diagonal elements, this means that off-diagonal elements are just complex conjugates of each other. And by off-diagonal elements, that means that like 2, 1 is just the complex conjugate of 1, 2. Okay, so there's not much to this. This is actually kind of trivial. It's already defined up here. I mean, you should know that when you flip, at this point, remember I told you this identity is a big deal. You got to remember that one. All right, now let's do a different one. Let's say that the operator is the A operator such that that A operating on these A sub n states, that the A sub n states are eigenstates, right? So you see the eigenvalue equation. Operate on the state and you get an eigenvalue times the state. Maybe the A is Hermitian as well, and that would make A to the n be a real number. And if that's the case, what I want to point out is that what you're going to get with, let's look back at A2. So let's look at this one, this off diagonal, this 2, 1 state right here. So that's A2, A operator, A1. Okay, now let's associate the operator acting on the ket. So that would be A1, the eigenvalue, A2, A1, oh, that is 0, right? That is 0. Remember that, let's say that A is Hermitian, then the states don't overlap, right? So the ground state has nothing to do with the excited states other than they span the same space. The projection of the ground state into an excited state is none. The ground state is not an excited state, so the projection is 0. Okay, now what that means is the representation of a matrix of the A operator in the basis of its own eigenstates. Well, let's see. Okay, the first state will be would be A1. The next state would be A2, and the off-diagonal elements are all 0. In fact, they're all 0, right? So that's what that means. Now, this is what you call a diagonal matrix. And that means that the 1, 1, 2, 2, 3, 3, 4, 4, those are finite and everything else is 0. All right, so that's how we recognize that an operator is being represented in its own basis set, because the matrix representation of that operator is diagonal. And that's kind of an important concept. Now, this is probably just a little too abstract, right? So let's work an example and let's do our spin deal, because spin, this is why we do, the book is focused on spin so much, because it really is going to make things easier. We'll move on to harder stuff later. Let's see. Okay, so we are going to do a spin deal. Okay, how about SZ? Excuse me. I'm staring at my notes. So SZ equals what? So let's generate a matrix for SZ. Okay. Now recall we talked about this last time, that matrix, and I think I used A, can be represented as a sum of all of its states, eigenvalue of that state, outer product. And notice also, you notice how that's diagonal, right? Okay, now let's apply that to SZ. Okay, so therefore, therefore SZ operator is, okay, so let me write it out in ket form. So it's h bar over 2, let's see. Okay. All right, now let's do the sum. Now in spin, there's only up and down. Okay, an outer product. Outer product of however many states, and there's only 2. There's only plus. Okay, eigenvalue, which is h bar over 2, that's this, the magnitude of spin in the up direction, and the outer product of that state. Now the other deal, the only other state is minus h bar over 2, that's its eigenvalue, and of course it's minus. Okay, so that is the SZ operator. Now let's put it in matrix form. Okay, now to put that in matrix form, let's see here. Let me, how much room do I have? Okay, I'll do it like this. Okay, now it seems that I've got to do plus SZ plus. Okay, that one's easy. And of course the lower one has to be fully symmetric. Okay, that's not hard to figure out. Now let's see here. Now I've got to remember that when I'm going down, it's the bra that changes. Okay, now there's only one way for it to change. Plus can only turn into minus. If the bra is changing, the ket is the same. And then this just does the exact opposite. Okay, now let's look at this. Now if I simply insert SZ into every one of these, as much as that may look a little daunting, it's actually, you should be able to do it in your head. Plus, there's no interaction with minus. plus plus simply returns an h bar over 2. Minus is okay here, but plus on this side is not. And minus acting with this, a minus ket with this plus bra, that nope, no, that's just a bunch of 0. Okay, minus plus, okay, minus doesn't work here, it works here. But plus on this side, no, that's nothing. Minus minus, okay, doesn't interact with plus plus, but it interacts with minus minus. And it looks like I'm going to get a minus h bar over 2. Okay, so is equal to h bar over 2, 1, 0, 0, minus 1. Okay, so there you go. So that's how you deal with it. And yeah, not too bad. Okay, now I'm going to go ahead and jump a little bit ahead, and as much as, you know, you've seen, we've already done some stuff with spin. Now you see how to create a matrix. So what? I mean, so what, really? I mean, it's cool you can write it down, you can show off that you can write it down, but so what? Okay, now it turns out that you're going to hear this term. You're going to hear diagonalizing a matrix. You're going to hear the eigenvalues of the matrix. What the heck does that mean? Well, let me point out something. Now I'm going to use a little bit different notation than you've seen before. I'm going to use notation that's more familiar for matrices, and what I'm going to do is I'm going to operate on SC times a wave function, and I'm going to return eigenvalues times that wave function. Now I'm using lambda for eigenvalues here, and that's because that's what you tend to use for matrices. And I know that's stupid. It's stupid, but that's how we do it. We have different letters when we're talking about matrices. Anyway, get used to it. Let's see here. Now, if you don't mind, let's ignore the h bar over 2. Okay, so what I'm going to do is I'm going to write the SD matrix as this. It's just a little bit easier. What you can do is just multiply all your results by h bar over 2 when you're done. It literally is that simple. Okay, now let's multiply it by the wave function, and I don't really know what it is. Okay, let's just call it AB. Okay, now if I subtract out the eigenvalue times that wave function, I better be 0. All I've done is I just brought this over to the left. Okay, now it turns out there's a theorem in matrix math that you can imagine that this is a very specific mathematical statement. It may or may not be true. I could certainly set this up. However, I set it up to not be answerable. It turns out it is answerable, but only under one condition. So for this to be true, it must be true that the following is correct. The determinant of the matrix minus the identity times the eigenvalue is equal to 0. Okay, now so what I've done is I've taken this matrix and I've subtracted lambda times the identity. Now the identity matrix, so let me write that out. Minus lambda times the identity matrix. And identity matrix is just diagonals are all 1. And so that is 1 minus lambda. I'm writing down the same thing, I don't know why. Okay, so that's what that is. The determinant is equal to 0. Now again, I can't emphasize enough, if this isn't true, there's no solution to this. All right, now, so if this is true, then we have a solution. It turns out that we can actually solve the problem just with this. I don't know why that works out, but it does. All right, and I'm hoping you remember what a determinant is. Diagonal minus the other diagonal. Okay, so therefore, 1 minus lambda times minus 1 minus lambda hold on, let's do that real quick. Lambda squared minus lambda, hold on, minus lambda plus lambda, that's 0, 0 lambda, minus 1 is equal to 0. Therefore, lambda squared is equal to 1. Lambda is equal to plus or minus 1. And those are the eigenvalues. Hey, that's actually it. Those are the eigenvalues. So, the eigenvalue of SZ in the SZ basis, and that's plus and minus r plus or minus 1, but we ignored h bar over 2. So if you hadn't, the eigenvalues are plus or minus h bar over 2. I didn't want to have to write h bar over 2 like a thousand times. Had I not just set like h bar over 2 equal to 1, this is what you would have gotten. Okay, so there you go. There's an example. Okay, now when you solve for the eigenvalues, you can then solve for the eigenvectors. Okay, and the way that works is, let's again work in a world where h bar over 2 is equal to 1, 0 minus 1. Now the way that works is you have to solve for each one individually, a, b. And of course this represents the plus and minus state. And these are like some kind of weighing coefficients. And let's do for lambda equals 1. Okay, so lambda equals 1 multiplies the right side by the number 1, so it's just AB. So the matrix times AB is equal to AB. Okay, now it turns out that the only way to do this is for B to equal 0. This doesn't work unless B is equal to 0, and therefore A is equal to 1, and therefore the one eigenstate is plus, and then likewise the other is minus if you solve for the lambda equals minus state. See, the eigenstate associated with lambda equals h bar over 2 is the plus state, and the other with the lambda of minus h bar over 2 is the minus state. That's how you do this. We'll probably do some more examples. Let me point out what you really do with this is you would diagonalize the Hamiltonian matrix with atomic orbital basis. And why you would do that, you would get molecular orbitals of O2. Okay, so what you would have is like oxygen 1, Hamiltonian, oxygen 2. So you're working in the basis of the individual atomic orbitals, and you would build a matrix, and the diagonal of the matrix would give you the energy levels, and the eigenvectors would be the molecular orbitals. So I may have shot over your head a little bit, but that's the idea. And even if I showed over your head, we just saw this, and this really hopefully wasn't too hard, right? Okay, so anyway, so neat stuff with matrices. Matrices are actually pretty awesome. I really like doing quantum mechanics with matrices. It just really is way easier. Let's see, I got about 20 minutes left. Now what? Okay, here's another ID. You need this. This is going to be one of your homework problems, so it's a bit of a pain. If you have two operators multiplying each other, and this is going to be very important when we do uncertainty principle, you can say that it's just its own operator. That's fine. Okay, so therefore, a matrix element, let's look at a matrix element. What that would be is, of course, XY. You're going to be doing, there's one problem that you're going to do, I think, on the present problem set, so maybe you've already started looking at it. That, I mean, to be blunt, is pretty frustrating. I mean, hopefully none of this looks terribly hard, but I told you that it has a difficulty that's unique. A double prime. All right, so I'm just trying to show you how you represent this. What we're going to do is insert an identity in between the two operators. Okay, so that's how you would handle that. But now we have a bit of an issue here, which is that we got to start talking about bras. All right, so a ket is a column vector. An operator times a ket is another ket. So none of this is particularly weird. But now, how do you represent bras with matrices? Especially because, you know, we got to figure that out at this point. Okay, as in all things, we're going to learn by doing. So I am going to pick something. I am going to just create a problem. I'm going to call it a prime operator gamma. Alpha state. So I've got an operator operating on the alpha state, and then I'm going to project onto that into some specific eigenstate. Okay. All right, now a bunch of hints. You should again recognize that this is actually an inner product, that this should be a number. This should be a scalar number. It should not be a vector, it should not be a matrix, it should be a number. All right, now to deal, I'm going to resolve an identity. Equals 1 to infinity, and I know where to put it because I've been doing this forever. And again, we're going to build you up so that you just kind of intuitively know where to put these things. Okay, now let's see here. What is this? Okay, this is clearly a column matrix. Now that's because remember that the bra increases as you go down. So notice I've got a sum of n to the however many states are in this representation, this basis. That's a bra, and the bras always increase going down a column. So in other words, this is A1 alpha, and these are inner products, so these are numbers, but I've shown a bunch of examples of that. Okay, so these are a bunch of inner products. Dot. Okay, now what about this? Now I bet you're looking at this and saying, oh, well, that's an operator, so therefore it's a matrix. Well, I don't think so. Now, for one, a matrix times a column vector is another column vector, right? So that's actually an operator acting on a ket and giving me back another ket. But that's not what this is. This is an inner product. This is a number. All right, the next thing to note, a matrix has to have two things changing. You gotta be changing on the right, and kets increase as you move this way to the right, and bras increase as you move down the column across. So again, kets move up, kets increase across a row, bras move up as you go down the column. But this is finite, right? I've just got the A1 ground state is our bra acting on the left, and there's only one of them. Okay, that means that this guy is actually not a column but a row. A row where the bra element is always A1. Now the ket goes A1, A2, A3, dot. So this is not a matrix, despite my operator. I see an operator, I just want to say it's got to be some kind of matrix. It isn't. It's actually it's a row vector. Okay, so what does that look like? Let's see here. This would be A1, operator, A1. Now again, a ket increases to the right. Okay, so there you go. All right, now notice that when you've got, I hope you remember your matrices, the result of a row and column matrix is this times this plus this times this, plus this times on and on and on and on and on. And the result is a number. So you end up with a number. Maybe it's complex, but whatnot. Okay, so therefore, if an so I hope I've convinced you that kets are column matrix, or column vectors, sorry. Got to be careful. We should not call single element matrices. We should not call them matrices. We should call them vectors. Anyway, a vector is a single element matrix. I'll try not to call it that way. That can be confusing. Okay, now kets are vectors, column vectors. Is a col vector. Okay, then let's do a bra. And I better, okay. Had to think about it. I tend to point the thing in the wrong direction. I better do the transpose. Is a row vector. Okay, so great. Abstract, huh? Let's make it concrete. Okay, let's go back to our Stern-Gerlach experiment. Let's take a state that's SZ plus, right? So we had some silver atoms. They gone through a Stern-Gerlach, and we blocked the spin down guys, and we only kept the spin up. All right, so I've prepared a pure state in SZ plus. Okay, but now I'm going to run it through SX. Right, another Stern-Gerlach apparatus that measures the spin in the X direction. I already did Z, in the X direction. Okay, that's fine and good. And now what I'm going to do is I'm going to measure the polarization in the plus direction. And let's do another one just for the hell of it. Now I'm just gonna say, again, I've built this thing to generate SZ plus atoms. I'm gonna run it through SX, and what I'm gonna do is I'm gonna measure whether it's retained itself in the plus state, SZ plus state, or whether it's gone down to the SC minus state. So notice how these quantum mechanical, these Dirac notation expressions, I can correlate that to an experiment. Okay, now we have not covered this. This is tomorrow's lecture, but I like to preview so that you get used to how this stuff looks. This is the SX operator, and it will make sense. Remember how I just talked about how what you do is you sum the possible states times a weighing coefficient. And it's about a 6-step proof to show that this is the SX operator in the SZ basis. It's not terribly hard. I'm going to do that next time. I just want to go ahead and show you this now and do this operation so that we can understand a little bit better about what all of this means. Okay, so let's see here. Okay, let's do plus SX plus, let's do that one first. Okay, now to understand how this works, I'm going to resolve an identity. Now the sum of states, my notation here is kind of stupid, but n goes from plus to minus. That I don't really have any other way to put this. I have no idea if this mathematical terminology is correct. SX, okay, here is our spin up or spin down state. Here's where I resolve the identity. Okay, now let's do this one first, right? I know that's a column matrix, and that will be 2 by 2. Okay, that will be, the first one is plus. I've defined the initial state as plus. The next element is minus, but the first state, the state I've created is plus. Okay, so there's the column. Now what about the row? I have to give myself a little bit more room. That is plus SX plus, the next element is plus SX minus. Okay, and the result is this times that plus this times that, so it's a number. Okay, but now let me put numbers to these. Let's see here, what have I got? Okay, plus plus is 1 because it's normalized. The projection of the plus into the minus state is 0 because the plus is not the minus state. Remember, that's just one of our Dirac rules. I'm defining that, so there's nothing to derive. It's an is. Okay, now, what about this thing here? Okay, let's look over here. Okay, plus plus. If I act on the right with plus, then this guy's okay, this one's not. Plus minus 0. Okay, now I hope you follow along, but this is 0. Because if I apply, where do I want to do this? Okay, plus, sorry. Plus, I confused myself. Plus, minus, plus, that's 0, plus minus, well that's 0, okay, 0, 0, everything's 0. Okay, so the first element is 0. Okay, let's look at the next element. Let's see, now this guy I think will survive. Actually, it's going to survive right there. All right, so I've got plus, minus, so there we go, that survived. This element survived. The next term is plus minus, okay, that's already 0, plus minus, that's definitely, so that's double 0. Okay, so this ends up being, what is this, h bar over 2. And what do we got? 0 times 1 plus h bar over 2 times 0, okay, that's 0. Okay. Plus Sx plus is 0. Okay, so Stern-Gerlach prepares atoms in the polarized plus Z state. I then measured what the heck is going on in Sx. I made my measurement, and then I've measured, I've queried how much are still spin up or spin down in the Z direction, and it turns out that even though I started in the plus Z direction, there's the SZ destroyed the polarization, and now there's nothing left. All right, next one. Let's do minus Sx plus, and same deal, sum n equals plus minus, so that is minus Sx n plus. Okay, so it turns out that this is going to be, our column matrix is the same. This is going to be, let's see, where do I need some spare room here. Okay, so I need to look back here. I need to look here, and I need to do this. So I've got, okay. This first term is, oh, what am I doing? What am I doing? Sorry. Let me write it out. Minus Sx plus minus Sx minus. And what is that? Okay. Minus plus, so that's double 0 on the first term. And I've got minus plus. Okay, so the first term survives. H bar over 2. The next one, okay, minus plus, that plus is that plus, minus, oh, no, that's 0. Okay, let's do the next term, plus, minus, that survived, plus, minus, that didn't. Okay, 0. Okay, so 0. The column matrix is still, oh my god, I'm sorry, did you see that? 1, 0 still. So the result is h bar over 2. Okay, so what happened is the again, we prepared, we had an oven with a bunch of silver atoms. They survived the polarization. We polarized them in the plus, SZ plus direction. We then ran through another Stern-Gerlach that was turned 90 degrees. And look what happened. It actually destroyed that positive Z polarization and instead it projected it to the other direction. And we know that by querying the overlap of this new state. What's its overlap with the spin SZ spin down state? And it has some overlap. So in fact, if we worked in a world of H bar was 1, then this would be half. And so that kind of represents that half of these things basically got wiped out in the process of making this measurement. Okay, well, I'm seeing I'm about out of time. I just want to, just give you one more example that's actually a little bit easier. Maybe I should have began with this. Beta alpha, an inner product again. And let's resolve an identity. Beta, a to the n, alpha, where again this is a column matrix and this is a row. But to make this a little bit more clear, given how we figure out a basis state and then we're given some arbitrary state that can be described with that basis, like beta and alpha. So let me say that again, but let me be a little bit more clear with an example. We are doing spin up and spin down, so we have plus and minus states, so those are our basis states, and alpha and beta may be some kind of weird vector sum. All right, now this guy will be given to you basically, but notice that this guy is kind of turned around. Usually what I've given you I've given you coefficients that are the projection of this whatever state, this cat state, into the basis. And this is the opposite. So the way you actually deal with this is you just turn this around. A1 beta, complex conjugate. So again, this is the row, the effect of the bra is to be a row vector. I just want to put it in terms, I want to project beta into that basis. You just have to remember that it's a complex conjugate. And however many states there are, I've gone to 3. And of course, there's the column matrix where I don't need a complex conjugate. It makes sense on its own. And A3, it better be symmetric, ... Okay, and again, this is an inner product, so it's equal to a number. Okay, folks, well, that's just really, I don't know that there was much of a coherent lesson as much as it's just stuff with Dirac notation. We're getting into some harder stuff, more advanced stuff. You've gotten a little bit more about spin up, spin down. Next time, we're going to do more spin up, spin down. I'm actually going to define the SZ. SZ is easy. We're going to define SX and SY, and then I'm going to set you up to do some of your homework problems because, again, I hope this hasn't been too difficult, but some of these questions can really throw you for a loop, especially when you're doing transposes and complex conjugates and whatnot. Alrighty, one more lecture like this and we're back in business on Monday. I will see you all then.